So the other day, you're in a very important meeting because you're a very important developer. This is annoying. Sorry. And somebody brings up, oh, well, our app is too slow. Maybe, you know, we should rewrite it in JRuby. I heard JRuby is faster. And you go like, nah, JRuby, no. And you're in that meeting, you just whip out your laptop, and for some reason, something in your application really depends on sorting something in a descending order, a bunch of numbers. So you write up this quick script, and you're like, okay, I get an array of numbers, and then I want to reverse sort them, so I do use the custom sort with a block where I exchange item and other. And I'm like, okay, let's see if JRuby is really that fast, as people always say. So you whip it out, and you go like, okay, let's use my Ruby 2.4.1, and let's just time the invocation of the script, and then do the same thing with JRuby. And as we can see here, or maybe you can't because it's farther gone, but with Ruby it takes me 0.15 seconds, and with JRuby it takes 3 seconds, 0.5. So that's it, done, right? JRuby is much slower. But then maybe your colleague is there and it goes like, oh, well, in this meeting, but I've heard JRuby has a very, very bad startup time. You go, oh, okay, what? You know, I got this. There's something called benchmark in Ruby, so I'll just use that. I'll use benchmark, I'll require it, and then basically the same thing. Next invocation, we do the same thing, but this time with the built-in Ruby benchmark library, and we see that for CRuby, we end up with a real time of 0.00381, and with JRuby it's more than 10 times slower because 0.004. And so, in the end, success, right? Those people with the JVM, they were wrong all along. Like, CRuby is the best thing, nobody needs to use the JVM, it's just expletive. Okay, end of the talk, because obviously benchmarking is very, very simple and all of you can do it. Thanks, yeah, that's, go have some beer now. No, for me this is really, I have no idea what I'm doing. This is not a good practice in a good way, and I'll give you a few reasons why. So first was way too few samples. We just had like one invocation of that method. That's the only thing that we did. Again, is that realistic data? We just chose an array of 1,000 numbers, and that array even was not realistic data, it was pre-sorted. Some sorting algorithms have the worst case performance if the data is pre-sorted or whatever. So that was not a good thing as well. There was no warm-up. I'll go into more detail about warm-up later, but most of us write web applications. The startup performance at the beginning is not as important for us because some virtual machines optimize, and so for us the most important thing is not the performance in the first minute, but in the 5 hours afterwards or the 3 days afterwards, and some implementations get much faster then. Also, this was just done on a work laptop in some development environment. It should always be done in a production environment. Also, the creation of the array was within the benchmark. Does the creation of the array matter in that case, or do I already have the array in that method? I don't have setup information, and worst of all, I did it on my laptop in a meeting, which means it ran on battery power, which means the CPU is downscaled and everything, and we have way different performance characteristics. And of course, also because I was in a meeting, I probably had Slack open, and that killed 50% of my performance already. Okay. So what's a better way to do this? So we can use what I would call a proper library, which is benchmark IPS, which some of you may know. And here you can also see what I did is I took the creation of the array outside of the benchmark, and I also shuffled it so that it is randomly, that it's not pre-sorted, but it's in a random order to make it more realistic. And then I did the same thing down here, which is just, I said, benchmark IPS, do something, and that's all fine. When I invoke that, first with CRuby and then with JRuby, and you can see it runs a warm-up before, so it actually is built for that kind of thing, because JRuby and Rubinius and Truffle, if you know that, really need that warm-up time. You can see that during the warm-up, it was much slower, and I'm sorry, some of the graphies, some of the boxes are off. This is not my laptop, so this is the wrong font, and so the wrong font size, but you should see downstairs that now it's much, much faster, but maybe you see it on the next slide. No, you don't. Okay. Well, we'll have to work with that. Above is the CRuby example, which says it did 1,600 iterations per second. So here, obviously, higher is better. And JRuby did In its warm-up, it did about as many iterations per second, but after the warm-up time, it did 2,400, so it was faster in the end. So now it's the end of the line again, so JRuby is obviously better again. Wait a second. How do we know that how we're reverse sorting the array is actually the fastest way to reverse sort the array? So here I prepared 3 different variants. The first one is the one that you already know. We use sort with the custom block. Then we just do array sort and then just reverse what we had. And then we do sort by, and we do a little trick. We do sort by minus the value. Because if I have a bunch of numbers and I want to sort them in a descending order, I can also just sort by minus the value of that number. That also works. And now a little participation on your part. I will go through each of them and ask who thinks which is fastest, and then we'll see who is right and who is not. So, who thinks that the first variant that I showed so far is the fastest way of actually doing this? Nobody? Well, one person does. Okay, with that intro, I'm not too surprised. Okay, oh sorry, yeah, first version. Second version, who thinks this one is the fastest? About a third of the room, I would say. And who thinks the sort by trick is the fastest? The other third of the room, and I think a third is then getting and not taking part. This box should actually be at BM compare because we compare the results, but that's the surprise thing when your laptop doesn't work. And what's fastest? Dot sort dot reverse is fastest. Congratulations to everyone. And it's faster by like a huge margin. It's almost 5 times slower, 5 times faster than sort by, and almost 7 times faster than our initial implementation, which used sort with the custom block, which for me was quite surprising when I first found out about this, because I would have actually thought that maybe sort by minus value is the fastest because it seems so tricky and cool, and then it would be the sort of the custom block because I'm just invoking sort of the custom block, and I would have thought that just sorting and reversing seems so simple. It seems too simple. I would think that that is the slowest. But maybe that's why it's the fastest, because I would imagine that in C Ruby, sort is probably implemented in C itself, and so maybe also reverse is implemented in C itself, while the other methods require custom blocks, so they can't be fully implemented in C, which might be the reason. Also, and also for comparison, here are the JRuby numbers, and here we can see something else that is, for me, quite interesting. For C Ruby is faster with the dot sorted reverse, but slower with every other variant. So that's also something that happens quite sometimes, that the performance characteristics of different Ruby implementations are different. So I'm sort of sad I chose that example because in the end C Ruby wins, and in most other benchmarks that I do, and I do a lot of them, JRuby is almost always at least 2 times as fast as C Ruby. But for the full disclosure, that's that. I'm also gonna, interestingly, this is Elixir. This is Benchy, a benchmarking library that I wrote on Elixir. I'm showing you this now for 2 reasons. First, also in Elixir, sort reverse is the faster way. And secondly, during the course of the presentation, I'll like to show you some graphs and some other stuff which I just have no tool in Ruby to show them to you. And I just hope and think that you're interested in Elixir so that you not get bored by me showing off my cool Elixir library. If you do, well, you can complain to me afterwards. So, as I said, cool graphs. So you can see here sort reverse is the fastest in Elixir as well. But then the fastness or the degree of fastness between sort by and sort of just a function changes afterwards. So after that very short introduction, this is the talk. How fast is it really benchmarking in practice? Toby, you can find me on the interweb as Practop. I run the Ruby user group in Berlin. I write that nice benchmarking library. If you've ever used Choose, a GUI toolkit for in Ruby, you should definitely try it out. It's in JRuby, the new version. It's pretty cool. I started maintaining SimpleCoff because I wanted to give it JRuby support, and then there were so many open issues, so I took a bunch of work, and I do lots of things. Also, I'm an engineer as a senior engineer at Lifery, where we have a Rails application and a couple of Elixir applications. What we do is same-day delivery, mostly for business partners. So they come to us and want, like, I want to have a package delivered between 19 and 21 o'clock, and then we go, here we go, and we do route planning and everything. It's quite cool. Okay. About this talk, For talks, oftentimes there's sort of a fight or rivalry between explaining a concept and showing some tool usage. When you have talks that go purely about the concept, you don't know how to apply it in practice. And if you have talks that are purely about the tool, you tend to focus too much on the tool, and you just learn how to use the tool, but not the real concepts, and you can't apply it to anywhere else. I try to marry both here, so I'll show you concepts and then show you actual tool usage in Ruby and or Elixir to do that, much like Yelena did in her talk. Before we go further, there's also something that we have to distinguish is a distinction between profiling and benchmarking. We'll talk about benchmarking here, which is seeing how fast something is, so something performs, and profiling can give you an overview, for instance, of what's wrong somewhere, what is slow, where is most of the time spent. What you see behind me is the call stack trace view of RubyProf, which is an excellent tool to do profiling in Ruby. And you can see here, this is my this is a Go engine I wrote for playing the AI game of Go. And you can see for a whole Monte Carlo tree search, which is the major algorithm there, where I spend most of my time. And this is very valuable because you can see that I spend 60% of my time in generate move, and I spend 30% of my time in set move. So knowing this, I know that it would be very good for me to benchmark these two methods, because any improvement I can make to these two methods, to these overall methods, really outruns everything else that I do. But I don't have the time to go into profiling too much because I can already talk so much about benchmarking. But it's something you should look into. And as I said, it's the RubyProf call stack visualization that helps me the most, because some of the other visualizations are not that helpful, to be honest. At least not for me. Something else that you need to do or should do is application performance monitoring. This is a screenshot of Skylight, but you can also use New Relic or something, because that's also where you see which endpoints are slow and which endpoints are used a lot. Because that's something very, very important, that if you care about the scalability of your servers, most of the time you have one endpoint that gets about 80% of the traffic or 60% of the traffic. So every minor improvement you can do to that endpoint really outweighs all the other improvements, just because it's hit so much by users. You would have to make another endpoint 10 times faster if you care about scalability of your servers than that one endpoint. So what do we benchmark in the end? Which means, what do we measure? Do we measure runtime? Do we measure the memory? Do we measure the throughput, or some custom thing? What is some custom thing? One of my personally most favorite benchmarks with a custom thing at all is the Phoenix benchmark, where they tried to reach, or where they reached 2 million WebSocket connections on a single server, and they started out as 100,000. There, the benchmark was just like, how many WebSocket connections can we have connected to the same server at once? And it's a brilliant benchmark for them. Afterwards, they also tested how much time it would take to distribute a message to all these clients. It was still about 1 second, so that was pretty damn impressive. So that's a good read if you're into that. We'll talk about runtime here, because runtime is what most people care about these days, and it's also the easiest to measure. There are some tools for doing some memory measurements in Ruby, but I'm not that familiar with them, to be honest, and runtime is mostly what we care about, because RAM, we just buy a new RAM stick, push it in the servers, and it's fine, or just buy a new bigger VM. So, but why? Why do we want to measure runtime again? First, that's what we saw before, we want to see what's fastest. We always, even though we are Ruby programmers, so we know we're not using the fastest language, there's still that urge to say, okay, what's fastest? How can we make this faster? And people give cool talks about that or whatever. Another thing that I really would like to know is how long will this take? So for instance, for my benchmarking library, I sort all the raw runtimes that I get to compute statistical values. It's just easier if I just sort it. There's a more efficient way that I could do it, but I wanted to see, do I need that? And I checked, and even with 1 million entries or something on my computer, I take a bit more than a second. And I think that's still acceptable for my users, that they wait like for a second for this to be sorted and then to do my computations, so that I don't have to get some totally fancy algorithm. And the other question that we often ask ourselves, or that I mostly use in my work, is, did we make it faster? So often we commit performance improvements, but for me that doesn't cut it. I want you to prove to me that you really made it faster, and you made it faster to a significant degree. And that's also why I write benchmarks. So at that point, some people might be like, hold up, Toby. isn't that the root of all evil? Like I heard that somewhere, like that's like pre-merge optimization, something, root of all evil, rings a bell, right? So for me, it's more like not reading the sources is the source of all evil, because that thing was actually said, that's true. We should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil. Donald Knuth, one of the like grandfathers of computing in 1974. But, so people just take that, put it out of context, poke it on a stick and be like, yep, we don't do performance optimization because Donald Knuth said so and he's cool. But if you read the original paper and just read the very next sentence, he says, yeah, we should not pass up our opportunities in that critical 3%. A good programmer will be wise to look carefully at the critical code, but only after the code has been identified. For the identifying the code part, we are again at profiling and application performance monitoring. And also in the prior paragraph, what Mr. Knuth said is that already a 12% improvement easily obtained is never considered marginal. And therefore, we should do it. Another thing that he outlines is that oftentimes our judgment or a priori judgment is bad and our intuitive guesses fail, which for you, for about half the people, was at least right with the reverse sorting example. So we need to prove it, we need to measure. All that said, benchmark does not equal benchmark. There are many different types of benchmarks, and I personally like to liken them to the testing pyramid. And the font again, nice. So in the general testing pyramid, we have unit tests that test the smallest units, mostly rather independently. We have integration tests where a couple of components work together, and then we have feature tests or end-to-end tests, something like QGAMP or Capybara, where like an actual browser is running around or we make actual requests against our API. And I see the benchmarking pyramid as follows, and this is not an official thing. That's something that I thought of. I saw parts of that in other talks, but that's how I think about benchmarking. We have micro benchmarks. That's what you see the most, and what the sort reverse benchmark is, like a very teeny tiny method. It's very easy to set up, and you tell like, oh, this is happening. We have macro benchmarks, which is something where I would say a couple of components interact. I like to do, for instance, I like to take what happens in the controller and put that inside a benchmark, and that is a macro benchmark then. And application level benchmarks are independent, oftentimes even of the application. So there are tools like WRCAR and WRCAR2, which just send HTTP requests against the server and see how fast the server responds, what's the mean response time, what's the throughput, and so ever. And you maybe know this. This is some performance benchmark of different frameworks, and they just run the same tests against the server that is set up. Of course, I made a screenshot of the top, so Ruby is nowhere to be found because it's way down, where it's 10% or maybe even 3% of the top performance. But this is a test where they do, I think, 20 updates to the, like in the SQL database within one request. Within the database, it doesn't have to be SQL. But Phoenix is still up there in the second to last in that particular benchmark. So, talking about these different types of benchmarks, what are the benefits or drawbacks of each? As we go from micro to application, of course, the number of components involved gets bigger. If I just do sort reverse, that's the only thing I'll ever do. And the macro benchmark, I involve more components. And the application level benchmark, oftentimes I even have the HTTP traffic in between, the parsing of the HTTP answer, the parsing of the JSON, and also on and whatsoever. At the same time, the setup complexity involves, like my my benchmark that I showed you right now has almost no setup involved to it. But if you test an actual application, you need to have records in the database and everything. So, or maybe even, because especially if you want to do an application level benchmark where you have like a separate benchmark to a separate application, you want to run it on the virtual server, not on the same machine, because then the testing tool and the application will get in each other's way, performance-wise. Also, usually the execution time increases, but so does the confidence of the real impact. When I do my micro benchmark and I change my sort by minus value to sort reverse, I'm not sure if there's going to be any impact on the real performance of the application, unless really reverse sorting big lists is what I do for a living. And mostly you don't, because still we managed to do 1,600, I think, even in the first and the worst version, 1,600 iterations per second. That means we're in the millisecond level of execution time, and every call to the database will cost you way more than that. But at the same time, the chance of interference also rises dramatically, because if you have an application level benchmark, maybe something is wrong with the network that will impact your performance from the benchmark. You'll never know. And so whenever somebody shows you a hopefully nice looking graphic like this, they will tell you that there is the gold middle, and I'll tend to do the same. Micro benchmarks are still rather easy to set up, but you can still be fairly confident of a real value. But what I often do is I use them to get like a high level view of what I'm doing, and then I extract micro benchmarks for the little parts of that high level view that I want to make faster. So to give you an example for that, or for different benchmarking types, one of the favorite things that I once learned when Eric Michaels Ober, I don't know if you had the luck to be at that Baruch, gave a very good talk about writing fast Ruby with some examples how some Ruby code could be more idiomatic and faster at the same time. And one of my favorite takeaway was using string tr versus gsub. So we have some general string, some arbitrary string, and once we use gsub and once we use tr, just to change every space to an underscore. And tr is 4 times faster than gsub, because gsub works on the level that it can replace multiple characters, but whenever you just want to replace single characters, tr is the way to go. Still, probably if you don't do replacing of characters for a living, it won't impact your performance, but it's very nice to know, and it's a nice thing to keep in head, so to write generally faster code. Or especially if you're a library developer, you never know what sort of stuff people will pull with your library, so it's always good to be on the safe and fast side. But as another example from, I mentioned my Go AI before, a micro benchmark would be this one I have here for the scoring, which is I create a final game state, and then I just see how long does my scoring class take to score that particular type of game. And that's a micro benchmark because I have one component, I benchmark in isolation. The impact for the real thing might be high or might not be really high. Then I have another macro level benchmark which does a playout. So what a Monte Carlo tree search engine does is it plays random games up until the end and then scores them in the end. So that playout involves creating a new game and then making a random playout to the end, seeing what the end is and scoring the end result. So that is a very macro level, like lots of components are involved, but it's still not the whole thing. And then I have a application-ish benchmark which does the whole Monte Carlo tree search, which means it initializes a tree and then does 1,000 playouts in that tree, building up the nodes of the trees with the winning results to choose my move that I do in the end. And so that one, that one really uses everything, like it uses every piece of code that I wrote for that particular project besides the CLI interface to it. And so that does the whole application, so it's an application-ish benchmark. Because it takes so long, I wrote my own little benchmarking library for it because benchmark IPS gets bad when one iteration takes longer than a second. And also I had to configure very high warm-up time, 3 minutes in that case, and a very high execution time because we use I used this one, and you might have seen that, to benchmark different Ruby implementations against each other. And some of them, especially Truffle Ruby, take a very, very long time. So that's different Ruby implementations here, and we can, how many iterations per minute this time they manage. And you can see that C Ruby is pretty down below there, so is Rubinius. But, well, let's quickly go up here. But the old Truffle Ruby and the new Truffle Ruby top the rest of the class. And the new JRuby run in server mode and invoke dynamic, which is up there, is also pretty fast. And when you have these numbers, you can give some nice statistics around them. For instance, you can measure the speed up relative to Ruby 2.0, because the goal of Ruby 3, if you haven't heard yet, is to be 3 times faster than Ruby 2.0. So we can measure how far along are we already. And Ruby 2.4 is at, I think, 1.2 times faster than Ruby 2.0. But JRuby plus invoke dynamic is already more than 3 times faster in that particular benchmark than Ruby 2.0. But the newest version of Truffle Ruby is more than 8 times faster than Ruby 2.0. But it takes a gigantic warm-up time of about 2 minutes to reach peak performance for a very small code base. Like, I don't have any external libraries. I just use the standard library and the code that I wrote on my free time. And another nice statistic that we can get is see how fast are we relative. Like I did this benchmarks once a year ago and once again this year, and we can see how much did the implementations improve. We can see Rubinius actually got worse, like a lot worse. It's only at a fifth of its performance that used to be, and Truffle Ruby got over 2 times faster even compared to its winning result from last time, which is pretty impressive, I think. So, with that out of our heads, let's talk about what is good benchmarking. And I really want to stress one point before we dive deeper into that, is what are you benchmarking for? Does it even make sense? Is this really a critical part of your system? Is it really performance critical? I don't care, like we have endpoints that are used once every 2 days. Do I need to spend time to make those faster unless my users complain? I don't. There's better things for me to do. Secondly, please give me your system specification. So for the benchmarks I ran here, you will see that I used Ruby 2.4, Elixir 134, and you can see the specifications of my little laptop there and even the Linux kernel version I'm running on if you want to attack my computer. So, foremost, get a really interference-free environment, which I mean plug your laptop in. Really close Slack. I'm not kidding about this. I had on my machine, you can see it just has 8 gigabytes of RAM. I had a case where Slack was running wild in the background, and all my benchmarks were 2 times as slow as they were than when running without Slack. So really, also if you have a hungry IDE, so I use RubyMine, so if you use VI or Emacs, you're probably fine, but get that out of the way and just let the laptop do only the benchmarking. That's most important to get clear and good results. Also, you need a correct and meaningful setup. Performance tests don't mean nothing if you have not enough records in your database, because N+1 queries won't hit you hard if you don't have at least 1,000 records or something, or in that order of magnitude that they could load. So it needs to be a production-like setup always. And when I say production-like setup, I also mean that you don't run them in the development environment. So at our company, we created a performance environment that is very like the production environment, except for a couple of things that we don't have like in production, so that we can run it locally more easily. Because lots of things like classes are auto-loaded, the views aren't cached, like all of that stuff is not on in development, which makes it lots faster. Like I sometimes run them first in development and in the performance environment just for fun, and in the performance environment they're often 4 times as fast. Another problem that you have is that logging is turned on in development to the fullest extent, and sometimes all those logs, especially when you do N+1 queries in Rails, can really kill performance, so it might not be as bad as you think. So that is really critical. This one doesn't apply as much to CRuby or Elixir, but a little bit. But always make sure that there's warm-up time, that you give it some warm-up, because most of us write server applications, so applications are usually warm. What can also happen besides the JIT, the just-in-time compilation of the JVM or of the GraalVM of Truffle Ruby, Postgres has some caching built in. You maybe have some caching in your application, and there's also some other caches that hit. The CPU cache hits maybe when you're lucky. So that is also important. Another thing that you need to be aware of is the garbage collection. And in the Ruby world, it's pretty much accepted that at least for micro benchmarks, for those teeny tiny things, that you run them without without garbage collection. With garbage collection disabled or with garbage collection in between the different invocations. In the Elixir world, I still have to convince them. Why don't you do that? This is from Benchy, and you probably can see it, but this is the raw runtime. So these are the runtimes that are measured for enum enum each raw runtimes. It's really the runtime of each invocation as they occurred through time. And you can see, especially there to the end, there's some enormous spikes. And I don't have proof of it, but I will bet you a lot of money, or some money, that they are caused by the garbage collection, because then at some point we have enough garbage collection kicks in, that increases the time of an individual iteration, and that messes up your statistics. Something else that I've learned, or one of my biggest learnings with, I do a lot of benchmarking, is that the inputs matter. The inputs that you have are a bit like the skyline. They're very diverse. There's small buildings, there's tall buildings, there's white buildings, there's pointy buildings, and so is your input. And, wait a second, I'm still not done with that slide. And it's very important to not just take one input, like one gigantic list, and be like, okay, this is obviously fastest now. the performance characteristics of algorithms can change depending on the size of an input. So for instance, I have a very big benchmark of tail-recursive versus non-tail-recursive in Elixir and Erlang. And you can see that the tail-recursive function gets better, or better comparatively to the non-tail-recursive functions, the bigger the list gets. For instance, at first, it's slower, but then for big inputs, which I mean lists that have 1 million elements or something, it's much faster. And this thing hit me personally, which I will tell you about now, which is in Elixir, because it hit me in one of our Elixir applications. So that is actual production code or production benchmarking code from us. So we have an Elixir application that tracks the courier locations. Like they have an Android application, every 5 seconds we get their location. So far so good. And sometimes we want to get, or oftentimes we want to get the latest location for a courier. And I got an error on Bugsnag that was like, oh, this thing timed out. It's like 15 seconds because that's the longest time Phoenix, Ecto allows a query to run before it kills it. By default, it was like, whoa, a query that takes 15 seconds, that's not that good. Let's have a look at that. And we used, this is a real case that really happened to me. And this latest career location thing is a database view we created in our Postgres database. So far so good. And for these two variants, you got to see the only difference is the one below does an actual courier ID, is actually exactly that courier ID, and the other one uses a helper, which basically does the courier ID is in this list of things. So it's mostly the same, but not quite the same. So what did I do? I took this and I was like, okay, well, I made a benchmark of it. We had one courier that had 2.3 million locations in the application, but just because there was a bug, because the application, the app kept submitting locations. And so I used that as my guideline. And then I made a benchmark and I could see, okay, with courier IDs plus the order clause is faster than the latest courier location by far. You can barely see its graph. So I was like, okay, this is it. I'm going to change it to that variant and not care about it anymore. You can see the standard deviation is pretty high, but like, so what? Well, I deployed this, and the second I deployed this, I got lots and lots of errors like, oh, this query timed out, this query timed out. I was like, no, I fixed this. Like, how can this be broken? I'm not stupid, am I? And it's like, wow, what? So we wrote the release back because we were really being flooded with those. I was like, what? No, I benchmarked this. I'm good at this. Or I'm supposed to. This was a couple of months ago, by the way, so it's not that old. And so what it turned out is I didn't care about the inputs. I just was like, I just take the biggest input, the one that gets me the 2.3 million results, because I was like, okay, this is an SQL query. So obviously it will do the most work with when it hits the most entries, because I want to get the latest one of those. So why should I benchmark for just 200,000 or something? I thought I was pretty safe because I took the largest input that I had. So with Bench, I have a feature where you can say, okay, we have different inputs, and then all the benchmarking jobs will be run with each one of the individual inputs. So we have the courier ID of a courier that has 2.3 million locations, no locations, 200,000, and 20,000 locations. So far, so good. So we take that and we still have the same old benchmark. I just omitted the other stuff just for time that you can see. And then we run it with all of them. And the result is quite shocking. So this is still the old implementation. You can see the latest courier location is the slowest when we have 2.3 million inputs, but it is the fastest, and the highlights are off, but it is the fastest for 200,000 locations, 20,000 locations, and for no locations. And the worst part is, the things that are fastest for 2.3 million locations, so with courier IDs and full custom, these are much, much, much slower the fewer locations we get from the courier ID that's matching. And to this day, I don't fully know why. I have like a theory that I will share with you in a second. And you can see down there, the average execution almost takes 8 seconds or more for the full customer with courier IDs. And obviously, we have way more couriers that don't have any courier ID or don't have any location in our courier application. So we were hit with all of those requests that give me the latest location of this courier, and we didn't have any location. And so that's where all the errors came from. I was shocked. And in the end, I fixed it because before we had one index on courier ID and we had an index on time. And I just made a combined index that used courier ID and then time to get that. So my personal thought why it went wrong is it didn't use the courier ID index. I also did like an execution plan, and it didn't use the courier ID index. It used the time index. So I think it just went looking, oh, I have nothing for this time, or I have lots of stuff for that time, but not from the courier. And so it did a sequential scan on that, and then died on that, basically. But with the combined index, the full custom version, the highlights are off. With the combined index, the full custom version wins by a landslide for each and every scenario. And that was me wishing I had used my own inputs feature that I built in a couple of months ago, really for this task. I didn't, and I learned the hard lesson of rolling a release back on production. So that's something for functions, like if they use a database or not, please benchmark this. With multiple inputs, it could save your day. And something else while we talk about indexes, also measure the impact on the insertion or the update time for a particular record, because it might be quite high, the impact. So here, our insertion time after having the combined index and not the separate indexes got a little bit higher, but not much, so it was fine. So, I don't know who follows me on Twitter, but I promised some statistics, and I think it's important to see the results both for A/B testing and also for benchmarking. And I'll give it to you in a common language, which is programming, but it's still in Elixir because these are the actual implementations that I use in Benchy. So the average, it's just the total time divided by the iterations. Then we have something which is called the standard deviation, which is just like you sum up your sample minus the average, get a square, and then in the end you get the square root out of that divided by the iterations. And what is the standard variation? It's a measure of the spread of values. It's what you saw both in benchmark IPS and in Benchy when it said plus minus this many percent. It's how the spread is. And as you can see, there are all these spikes in the raw runtimes, which is the spread of the values. Here's another graph I draw in Benchy, which is a histogram, which basically takes the runtimes and puts it into runtime buckets. So the first bucket is from, I don't know, it's from 7,400 to 7,400. And so you can see basically how is it generally distributed. And you can see here, you probably can see it from the back, but there's very, very tiny little blue bars all the way up there. And those are outliers. Maybe the garbage collection got triggered or something else, which is why these exist. And what happens to those is they change the result. So they negatively impact your average. It might also be that maybe Dropbox wanted to get something or Slack wanted to get some messages, whatever. And this is actually an example of a very low standard variation. I think this had a standard deviation, of 8%. And also if you wondered in the graphs, the standard deviation is noted by these little black bars that shows sort of like how far does this deviate. So what can we do? Because it negatively impacts our average. There's a thing called the median. The median is not supplied by benchmark APS, which is something I'm sad about, but Benchy gives it to you, and this is where I sort the runtimes. The median is just like you take all the raw runtimes you measured, and you sort them, and then you just take the one in the middle, because you say that's like probably your most common value if we sort them. It does a much better job of getting rid of outliers. And if you don't have a middle, you just take the ones left and right and get the average. And what's the impact of that? So this is something with an standard deviation of, I think, about 20%. And we can see the average of that particular distribution lies about there. And from the distribution, we can see that that's not a typical value at all. It's way north of all the values that we get to the left side. Whereas the median sits there, and it's pretty much a typical value. And the other thing is it's also more resistant to outliers because the median isn't impacted as much. Like if I get one measurement wrong, that's maybe 10 seconds. The median won't change, but it will have a pretty big impact on the average, for instance. As one last goodie for the statistics part, who has ever seen one of these box plots? Who knows what they actually mean? Oh, very good. I didn't know until a couple of months ago until I implemented them myself, but I think we have a few academics in the room. So what do they mean? So the line in the middle is the median. And so the median splits the sorted distribution in half, and then we split the north direction and the south direction, basically, or the lower ones and the high ones also in half. And this is where the upper level and the lower level go. So that is basically the 50% that's most in the middle. So we see how are the values distributed here. And then upper level minus lower level, I would call it, is called, or well, those are the quantiles, is called the interquantile range. And every value that from the upper or lower level, up or south, still falls within the interquantile range is denoted by these markers that go out north or south. And everything that still falls outside of that range is qualified as an outlier. So it's a very nice thing to see how are the values basically distributed in the measurements. So I talked about benchmarking to you a lot now, and I know I speak very fast, but that's just how I am. I'm sorry a bit for that. This last slide, I just want to show you how I think about benchmarking and how it's expressed in Benchy. This is an actual interface that you can use in Benchy. So how do you think about it? I have some configuration for my benchmark. Then I initialize my benchmark with that configuration. Afterwards, I gather some system data. So Benchy also tells you you're running on this Elixir version, on that Erlang version. I would love for Benchy to also tell you what CPU you have and how much RAM you have. Then I define all the benchmarks that I have. I have a benchmarking job, which is a function that I execute. Then I measure all the raw runtimes. I have a separate step in which I gather all the statistics, the median, the average, the standard deviation. And afterwards, I can pass all this data, the raw runtimes, the statistics, the system. I can pass all of that to different formatters that give you console output or the HTML output, which makes this a very flexible system where you can exchange every layer as long as you adhere to the contract. And with that, I'll leave you. Please enjoy benchmarking. I hope you enjoyed this presentation. You can find Benchmark APS there. It's written by the lovely Evan Phoenix, and you can also find Benchy down there.
Thanks. And are there any questions?
No questions. If you have feedback, good or bad, please tell me, because this talk will also be given more in the future. Yes, Piotr.
My question is, when are those lovely graphs coming to Benchmark APS? I mean, you already wrote them in Elixir, and that's basically just, you know, kind of elitist syntax for Ruby, so they should be like easily transferable.
It is a very good question. So actually the input for them in Elixir is a JSON format that I defined, so I can do that. And Benchmark IPS also very new. There's benchmark.fyi, which works with every Benchmark IPS version 2.6 and up, which is a feature where you can submit your benchmarking results from Ruby to an online service, which also I think draws some graphs, but I haven't seen it yet because the last time I checked it out, it didn't work yet. And I actually told Evan, like, here, I use this wonderful library, you can use it as well, and here's an example of how I use all this, but he never replied to the conversation again, but he's still working again. But it is on my internal to-do list to have a look at the graphs that Benchmark IPS has, and maybe give them some of my graphs.
Excellent, thank you. So, once again, thank you so much.
Thank you for inviting us, dziękuję.